Well, friends, in electromagnetics, we mainly deal with electromagnetic field vectors, namely electric field vector and magnetic field vectors, their interactions and propagation in different types of media. The time varying electromagnetic fields give rise to an electromagnetic wave which propagates through the medium and can be used for several types of applications. One must know about some fundamental things about propagation of electromagnetic waves through different media, their properties, and some important phenomena. So, in this module, we will discuss mainly about the basic concepts and the derivations of wave equations. Actually, we are familiar with the concept of wave right from our undergraduate studies. We are knowing about some of the basic terms and some concepts. So, we will start our discussion with a brief and rapid revision of some of such basic things about wave motion. After completing this module, you will be able to know about different types of waves and modes of wave propagation. You will be able to understand the general derivations of wave equations for E and H vector and the wave equation for sinusoidally time varying electromagnetic fields. In addition, you will be able to understand the derivation of what is known as Poynting's vector theorem. Wave motion. When we think about these two words, there arise so many issues we have to attend for. For example, what do we understand by the term wave? What are different types of waves? What is the speed of wave? On which factor it depends? Does wave propagation need a material medium? Which changes occur in the properties of the wave when the wave travels from one medium to the other? How a wave is described mathematically, so on and so forth. Let us try to brush up our knowledge about some of these and some other issues one by one before we proceed to discuss about electromagnetic waves. What do we understand by a wave? A wave can be described as a disturbance which propagates with time. Wave can be described as the shape of the matter which appears to propagate with time. Here, the particles of the medium are oscillating about their mean position with different phases. What is phase? Phase is the physical quantity which characterizes the state of oscillation. What is meant by state of oscillation? State of oscillation of a particle signifies mainly the position and tendency of motion. In the case of a progressive wave, the phase of the particle is continuously changing with time. Wave motion implies propagation of energy in a medium. There are different types of energies. Accordingly, we may think of different types of waves. We may think of thermal waves, gravitational waves, etc. Some of such types of waves have been enlisted here. The waves on oscillating spring and sound waves consist of compressions and rarefactions and are classified as mechanical waves and acoustical waves respectively. Generally, wave propagation needs a medium. Can we have a wave which does not need a material medium? The answer is yes. We have electromagnetic waves. These waves can propagate in free space also. Light is an electromagnetic wave which is well known to us. Depending upon the magnitude, the whole range of frequencies and wavelengths right from 0 to infinity is subdivided into various parts such as radio frequency, microwave, visible region, UV, X-rays, gamma rays, etc. This classification is known as electromagnetic spectrum. The main regions of the spectrum are as shown. Generally, we classify the waves as longitudinal and transverse depending on the direction of vibration of the particles with respect to the direction of propagation of waves. In a transverse wave, the direction of vibration of particles is perpendicular to the direction of propagation of wave, while in longitudinal wave it is parallel. Waves on a spring, sound waves, are the examples of longitudinal waves, while waves on the horizontal rope or light waves are the examples of transverse waves. In transverse electromagnetic waves, the electric field vector and the magnetic field vectors are mutually perpendicular to each other and can be supposed to play the role of oscillating particles. Depending upon their direction of oscillations with respect to each other and the direction of propagation of the wave, we can have different types of electromagnetic waves. Let us see how to obtain a wave equation in one dimension. Consider a very long string stretched horizontally with tension T. When in equilibrium, let us assume that the string coincides with x-axis. Due to a small momentary stretch in vertical direction, the wave propagates along x direction. Consider a small segment of the string at x of length delta x. The net transverse force on the segment is given by F is equal to T sin theta 2 minus T sin theta 1, where theta 1 and theta 2 are the angles made by the string with x axis at x and x plus delta x respectively. Now, since the vertical stretch is very small, the two angles, namely theta 1 and theta 2, will be very small. Hence, the sine ratios of the two angles can be replaced by tangent ratios of the two angles. Thus, we have F is approximately equal to T into tan theta 2 minus tan theta 1. Let us call this equation as equation number 1. Now, tan theta 2 is equal to da by f by da by x evaluated at x plus delta x, and tan theta 1 is equal to da by f by da by x evaluated at x. Using this result in equation number 1, we obtain f is approximately equal to T tan theta 2 minus tan theta 1, which is equal to T into da by f by da by x evaluated at x plus delta x minus da by f by da by x evaluated at x. From calculus, we know the definition of second derivative of a function f of x t with respect to x, which is as shown. Da by 2 f by da by x square is equal to limit as delta x tends to 0 of the ratio da by f by da by x evaluated at x plus delta x minus da by f by da by x evaluated at x totally divided by delta x. Hence, da by f by da by x at x plus dx minus da by f by da by x evaluated at x is equal to da by 2 f by da by x square into delta x. Let us call this equation as equation number 5. Using result 5, in equation number 3, we obtain equation number 6 as shown. Here we get f is equal to T into da by 2 f by da by x square into delta x. Let us call this equation as equation number 6. Also, from Newton's second law of motion, force is equal to mass into acceleration, that is equal to delta m into da by 2 f by da by t square. Now, if lambda is the linear mass density of the string, that is mass per unit length of the string, then delta m is equal to lambda into delta x. It is the mass of the segment of the string of length delta x. Equating equations 6 and 7, we obtain f is equal to t into delta 2 f by delta x square into delta x, which is equal to lambda delta x into delta 2 f by delta t square. From this equation, that is equation number 8, we obtain one dimensional wave equation for a wave travelling with speed v as shown. Thus, we have delta 2 f by delta x square is equal to lambda upon capital T into delta 2 f by delta t square, which is equal to 1 upon v square into delta 2 f by delta t square, where v is square root of t upon lambda. One can verify that the quantity v really has dimensions of velocity. In 3 dimensions, the wave equation takes the form del square f is equal to 1 upon v square into delta 2 f by delta t square, where f is a function of x, y, z and t. We know that a sinusoidal oscillations of a particle is expressed as y is equal to a sin omega t plus alpha, where y is the displacement of the particle at time t from its mean position, a is the amplitude of oscillation, t is the time, f is the frequency of oscillation, that is number of oscillations per second, omega is 2 pi f, which is angular frequency, the units are radian per second, alpha is the initial phase or epoch, omega t is addition to the phase in time t, and omega t plus alpha is the total phase at time t. A sinusoidal wave propagating along x-axis with velocity v can be expressed in various ways. Y of xt is equal to a sin omega t minus kx, which can be written as y is equal to a sin omega t minus 2 pi upon lambda into x, where k is replaced by 2 pi upon lambda and is called as a wave propagation vector. Similarly, we can use the definition of omega, that is 2 pi f, and v is equal to f lambda. With this we get y is equal to a sin 2 pi vt upon lambda minus 2 pi upon lambda into x. By taking 2 pi upon lambda as a common factor, we can finally get y is equal to a sin 2 pi upon lambda into vt minus x. All these expressions are useful while solving problems when the quantities are either frequency, velocity, propagation vector, wavelength, etc. For mathematical convenience, electromagnetic waves are generally represented using complex form. A sinusoidally time varying fields or waves have amplitude and phase. Hence, they are generally represented using complex form as shown. Here, electric field vector, for example, at a point r bar at time t is given by E0 bar into e raised to j omega t minus k dot r, where k is the propagation vector. Similarly, the magnetic field vector h bar at r bar t is given by h0 bar into e raised to j omega t minus k dot r. This expression is highly useful because it is able to give the magnitude and the phase at one site. For mathematical analysis, this expression is used, and finally, the solution is selected as a real part or imaginary part of the complex solution depending upon the given type of the field. Let us think of electromagnetic waves. Electromagnetic wave propagates in a medium as a result of time variation of electric and magnetic fields present at a time in the space simultaneously. As a result of interaction of electric and magnetic field vectors, there arises a net propagation of electromagnetic energy in a direction perpendicular to the plane containing the two vectors. It is defined through a physical quantity known as Poynting vector S. It is given by S is equal to E cross H. It represents electromagnetic power flow per unit area. The SI unit of S are watt per square meter, that is joule per second per square meter. Whenever we are talking about propagation of electromagnetic waves, there are two types of energies involved. One is electric energy and the second is magnetic energy. How much is the energy stored per unit volume? That is, what is the energy density? That is an important parameter which must be accounted for. So, we must know about the expressions for them. It be remembered that electric energy stored per unit volume is given by 1 half epsilon into E square. With the definition D equal to epsilon E, it can be written as 1 half E dot D. Similarly, the magnetic energy per unit volume, that is given by 1 half mu into H square, which can be written as 1 half B dot H with the definition or the relation B equal to mu into H. These expressions are highly useful for solving some problems related with the distribution of electromagnetic energy. For example, in Poynting vector theorem, this expression will be used further. Another point which you should know is that whenever the electromagnetic wave is propagating from one medium to the second, what changes? Does the frequency change or wavelength change? We are familiar with the experiment that a ray of light is going from air to glass prism and it bends. What changes? Wavelength or frequency? Such questions which we might have encountered in earlier studies, they are very important. It be remembered that whenever electromagnetic wave travels from one medium to the other, its wavelength changes and not the frequency. Electromagnetic fields carry momentum also. The momentum density stored in the electromagnetic fields is given by P is equal to S upon C square, where S is the Poynting vector to be discussed later and C is the speed of light. We can derive differential equations which are known as wave equations for E and H vectors starting from Maxwell's equation. We assume the medium to be linear, isotropic and homogeneous. Vector identities discussed in one of the earlier modules can be highly useful in these derivations. Let us see how these wave equations can be derived. For wave equation in E, we have to consider the Maxwell's third equation, namely del cross E is equal to minus delta B by delta T. Taking curl on both the sides, followed by the use of vector identity, we arrive at the equation involving del square as shown. The equation is del of del dot E minus del square E is equal to minus delta by delta T of del cross B. The vector identity which we have used is del cross of A is equal to del of del dot A minus del dot del into A. Use of Maxwell's first and fourth equation and using the relation J equal to sigma E and D equal to epsilon E leads to the equation as shown. Del of rho upon epsilon minus del square E is equal to minus mu into delta by delta T of J plus delta D by delta T, which is equal to minus mu sigma into delta E by delta T minus mu epsilon delta 2 E by delta T square. Hence, rho is the volume density of the electric charge present in the medium, which may be 0 or may not be 0. If the medium does not contain any free charge density in it, then rho is equal to 0. Hence, we have the wave equation for E as shown, namely 0 minus del square E is equal to minus mu sigma delta E by delta t minus mu epsilon delta 2 E by delta t square, which is del square E is equal to mu sigma delta E by delta t plus mu epsilon delta 2 E by delta t square. Note that if the medium is non-conducting, then sigma is 0. Then the equation reduces to the equation, namely del square E is equal to mu epsilon delta 2 E by delta t square. Comparing this equation with the wave equation, del square F is equal to 1 upon V square into delta 2 F by delta t square, we understand that the speed of electromagnetic field vector is given by V equal to 1 upon under root mu epsilon. If the medium is a free space, we have mu equal to mu 0, epsilon equal to epsilon 0. With these, we get V equal to c, the speed of light. The presence of the term involving first derivative of electric field with respect to time indicates the loss of amplitude of electric field vector during propagation. In the case of a non-magnetic material, this is due to the conductivity sigma of the medium. Thus, mu sigma delta E by delta t, this term indicates damping of electric field, while mu epsilon delta 2 E by delta t square corresponds to the propagation of electric field vector. Thus, we understand that as the electric field propagates, there may be a loss of its amplitude. How fast will be this loss? It is decided by comparing the relative magnitudes of the displacement current and the conduction current term in the equation. On similar lines, starting with Maxwell's equation, we can obtain wave equation for H vector. For this, we have to consider Maxwell's fourth equation, namely del cross H is equal to J plus delta d by delta t, taking curve of both sides, followed by the use of vector identity and the relations d equal to epsilon E and J equal to sigma E, we arrive at the equation involving del square del cross H is equal to J plus delta d by delta t. Therefore, del cross of H is equal to del cross of J plus delta by delta t of del cross of D, which is del of del dot H minus del square H is equal to sigma into del cross E, but epsilon into delta by delta t of del cross of E. Note that we have made use of the same identity quoted earlier. Use of Maxwell's second and third equation and using the relation B equal to mu H finally leads to the equation del square H is equal to mu sigma delta H by delta t plus mu epsilon delta 2 H by delta t square. Note that if the medium is non-conducting, then sigma is equal to 0. Then we have the equation del square H is equal to 0 plus mu epsilon delta 2 H by delta t square, that is del square H is equal to mu epsilon delta 2 H by delta t square. Comparing it with the wave equation, namely del square F is equal to 1 upon V square delta 2 F by delta t square, we understand that the speed of electromagnetic wave vector is given by V equal to 1 upon under root mu epsilon. If the medium is a free space, we have once again as before V equal to c, the speed of light. The presence of the term involving first derivative of magnetic field with respect to time indicates the loss of amplitude of magnetic field vector during propagation. This is due to the conductivity sigma of the medium. Thus, mu sigma into delta H by delta t, this term indicates the damping of H, while the term mu epsilon delta 2 H by delta t square represents the propagation of H. Thus, similar to the case of electric field vector, we understand that as the magnetic field vector propagates, there is a loss of its amplitude. How fast will be this loss? It is decided by the comparison of the relative magnitudes of the displacement current and the conduction current terms. We have the wave equation for E and H vectors as follows: del square E is equal to mu sigma delta E by delta t plus mu epsilon delta 2 E by delta t square, and del square H is equal to mu sigma delta H by delta t plus mu epsilon delta 2 H by delta t square. Note the similarity between these two wave equations. From these equations, we understand that both the vectors, namely E and H, travel with the same speed 1 upon under root mu epsilon. Hence, we conclude that the electromagnetic wave propagates with a speed 1 upon under root mu epsilon, where mu and epsilon are the electromagnetic constants of the material. It can be shown that for sinusoidally time varying fields, the wave equations derived earlier take the following form: del square E is equal to gamma squared E and del square H is equal to gamma squared H, where gamma is known as intrinsic propagation constant of the medium, alpha is the attenuation constant, beta is the phase constant. Alpha is given by under root of j omega mu into sigma plus j omega E, and gamma is equal to alpha plus j beta. Clearly, gamma is a complex number, hence its square root will be a complex. The real part is alpha, while the imaginary part is beta. A plane wave is an electromagnetic wave where phase is constant over a set of planes parallel to each other. A uniform plane wave is a wave where magnitude and phase both are constants. Whenever a uniform plane wave propagates in a lossless dielectric medium, that is conductivity equal to 0, has the characteristics alpha, beta, eta and phase velocity Vp as shown. Alpha is 0, beta is omega into under root of mu 0 epsilon, eta intrinsic stand-off ratio is under root of mu 0 upon epsilon, that can also be written as eta 0 upon under root of epsilon r. Phase velocity is given by c upon under root of epsilon r, where epsilon r is the relative electric permittivity epsilon upon epsilon 0. We know that propagation of electromagnetic wave implies propagation of electromagnetic energy. The vector S is equal to E cross H is taken to measure the time rate of passage of electromagnetic energy per unit area and is known as Poynting's vector. Poynting's vector is given by S is equal to E cross H. The units are watt per square meter or joule per square meter per second. Poynting vector S represents the amount of electromagnetic energy flowing through unit area per second. Poynting vector theorem explains the distribution of energy carried by an electromagnetic wave while propagating through the medium. It can be briefly stated as follows: a part of electromagnetic energy is lost in overcoming the resistance of the medium, and the remaining energy remains stored in the medium as the electromagnetic energy. The theorem is known as Poynting vector theorem, which accounts for the energy distribution through the following mathematical equation. The equation is as follows: integral E cross H dot ds over the closed surface S equals volume integral J dot E dV plus delta by delta t of volume integral E dot d plus B dot H dV. Let us see how this theorem can be derived from Maxwell's equation using some mathematical theorems. We start with the Maxwell's third and fourth equation involving curl of E and H vectors respectively. Thus, we have del cross of E is equal to minus W by delta t, which is Faraday's law, and del cross H is equal to J plus delta d by delta t, which is Ampere's law. Consider an electromagnetic wave propagating through linear, homogeneous and isotropic medium. Then we have B equal to mu into H, D equal to epsilon E, and J is equal to sigma into E. Dot product of the two equations with E and H vectors followed by the use of vector identity yields the result as shown. Now from 1 and 2 we have H dot del cross E is equal to minus H dot W by W. Similarly, E dot del cross H is equal to E dot J plus E dot W by W. Subtracting 1 dash from 2 dash and use a vector identity, we have E dot del cross H minus H dot del cross E is equal to J dot E plus E dot W by W plus H dot W by W. Similarly, del cross of E cross H is equal to J dot E plus E dot W by W plus H dot W by W. Let us call this equation as 2. Note the identity we have used for converting left hand side into a term consisting of the cross product of del E and H. After integrating equation number 2 over volume V of the medium, we get volume integral of del cross E cross H over volume V is equal to volume integral of J dot E dV over the same volume V plus volume integral E dot W by W plus H dot W by W over the volume V. Left hand side of the equation can be converted to surface integral using Stokes theorem. After doing this, we get surface integral of E cross H over a closed surface S is equal to volume integral of J dot E over the volume V plus the volume integral of E dot W by W plus H dot W by W. Let us call this as equation number 4. Now, E dot W by W is equal to 1/2 of W by W of E dot D. Similarly, H dot W by W is equal to 1/2 W by W of H dot D. Thus, finally, we have from equation number 4 surface integral of E cross H over the closed surface S is equal to volume integral of J dot E over the volume V plus a volume integral of 1/2 W by W of A dot D plus 1/2 W by W of H dot B. Let us see what each term in the theorem represents. Here, the surface integral of E cross H indicates the total electromagnetic power carried by the wave, while the first term on the right hand side, namely volume integral J dot E, represents the power lost in overcoming resistance of the medium in the form of heat. Third term, that is second term on the right hand side, namely W by W of volume integral of 1/2 E dot B plus B dot H, represents the power stored by the medium in the form of electromagnetic energy. The knowledge of Poynting vector is highly useful in estimation of various quantities definable in terms of electromagnetic energy, such as reflection coefficient, transmission coefficient and absorption coefficient, etc. Electromagnetic waves may be characterized by polarization. The different types of polarizations are plane polarized, linearly polarized, circularly polarized and elliptically polarized electromagnetic waves. The terminology depends upon the direction of oscillation of the field vectors with respect to each other and the direction of propagation of the wave. If the direction of oscillations of the electric field vector, magnetic field vector and the direction of propagation of wave all are mutually perpendicular to each other, then the wave is called as transverse electromagnetic wave, which is abbreviated as TEM wave. The electric field vector is generally taken for describing the state of polarization of electromagnetic wave. The electric field vector E at a given point can be resolved into two mutually perpendicular directions such as x and y directions into two components Ex and Ey as shown. During propagation, either the magnitude and or phase of the vector may remain constant or may change. Depending upon this, we have different types of polarizations. If the direction of oscillation of electric field vector is confined to a line during propagation, then the wave is called as linearly polarized wave. If the direction of oscillation of electric field vector is confined to a plane during propagation, then the wave is called as plane polarized. If the tip of the electric field vector traces a circle during propagation, then the wave is called as circularly polarized wave. If the tip of the electric field vector traces ellipse during propagation, then the wave is called as elliptically polarized wave. Friends, so far we have discussed the basics of electromagnetic waves and wave motion. The concepts introduced in this module can be applied to discuss various phenomena like reflection, refraction at the boundary of two different media, and also the effects like total internal reflection, etc. We will discuss about these and many other phenomena in the subsequent modules. To summarize, we may say that an electromagnetic wave propagates with a speed given by 1 upon under root of mu epsilon, which are the constants of the medium. Time varying sinusoidal electromagnetic wave is characterized by a propagation constant which consists of attenuation constant and the phase constant, which are the functions of frequency. Depending upon the state of oscillation of magnitude and phase of the electromagnetic fields, we can have different types of polarizations, namely linear, circular and elliptical. The amount of energy lost and stored by the medium when the electromagnetic wave propagates through it is given by a theorem which is known as Poynting's vector theorem. Poynting's vector is the indication of amount of electromagnetic power per unit area. Whenever electric field and magnetic field vector propagates through a medium, its amplitude goes on decreasing because of the conductivity of the medium. Hence, the medium through which the electromagnetic wave is propagating is important. Thank you.